in the beginning of lesson 78, you would complete an investigation that will help you to come to this conclusion of how you can find the area between two curves marked by the function f of x, assuming it is above the graph of g of x, between an interval from a to b. If you have selected your functions correctly, then the absolute symbol that you see in this formula will not really be needed. But if you have reversed the order of the subtraction of the two functions, then this absolute values will give you the correct sign of the area that you're looking for. Let's take a look at example 1. We're going to find the area bounded by the curve f of x and g of x. And from the equation, both are quadratic. We know that f of x has vertex at 3 and 8, and it opens down, which means that the red curve shown on this graph is f of x, and the blue curve represents g of x in this case. Okay, and then the area shaded in shows what we need. So let's take a look at the starting point and the end point. With the graph, it's easy to tell that we're going to have to find the integral from 1 to 5. You can also do this algebraically. So let's start by setting f of x equals to g of x. I have negative x minus 3 squared plus 8 equals to x minus 3 squared. I can actually claim that 2x minus 3 squared is equal to 8, meaning that 4 is x minus 3 squared plus or minus 2 is x minus 3, making x equal to 3 plus or minus 2. Therefore, x is 3 minus 2, 1, or x is 3 plus 2, 5. Okay? Now, we're ready to find the area. So the area that we're looking for goes from 1 to 5, and the graph of f of x is above the graph of g of x, meaning that I can take negative x minus 3 squared plus 8 minus x minus 3 squared dx. Okay? What does this give me? This gives me negative 2 times x minus 3 squared. So x minus 3 squared itself is x squared, and then minus 6, so plus 12x plus 9 times 2, so plus 18 minus 18 plus 8 dx, which gives negative 2x squared plus 12x minus 10 dx. And so I will have the following. When I take the integral, I have x cubed over 3 multiplied by negative 2 plus x squared over 2 multiplied by 12, so that's 6x squared minus 10x. And I evaluate this definite integral from 1 to 5. 5 cubed is 125, negative 250 over 3 plus 5 squared is 25, 150 minus 50. Okay, and then subbing in 1, I have negative 2 over 3 plus 6 minus 10. Okay, simplifying this work, you have 150 minus 50 is 100, 300 minus 250, so 50 over 3. And then you have negative 4, negative 12, negative 14, so plus 14 over 3, which gives you 64 over 3 square units as the area bounded by the curve of f of x, g of x from 1 to 5. Here is question B. Okay. So this time, question B shows a cubic function and a quadratic function. If you plot this out, you will notice that there are two different regions that we need to look for. And what makes these two regions special is that, well, between -2 and 0, the blue function, the cubic function, is above the red function. But it changes when we go from 0 to 1. Now the quadratic is above the cubic. So we need to be careful, and we should calculate the area, and also, just to be safe, by separating the two regions from each other and add them up at the end, okay? If we don't have this particular graph here, then you will have to maybe use a few test points or, sketch your functions, find the point of intersection in order to figure out, which curve should be the one above, which one should be the one below, or simply use the absolute value signs, okay? Now, let's confirm the points of intersections by setting the two functions equal each other. So x cubed plus x squared minus 2x equals 0. I have x squared plus x minus 2. So this factor into x plus 2, x minus 1 equals to 0. So indeed, my cutoff points are as follows. Okay. So between -2 and 0, I know that the cubic function goes on top, which means I should be doing x cubed plus 2x squared minus x squared minus 2x dx. And then from 0 to 1, I should switch. I have x squared plus 2x minus x cubed minus 2x squared. Okay? So it just becomes integration now. Okay, so x cubed becomes x4 over 4. I have 2x squared minus x squared, that's 1x squared, plus x cubed over 3, minus 2x squared over 2, so it's just x squared. This from -2 to 0, plus this time I have negative x cubed, so negative x4 over 4. I have x squared minus, so minus x squared becomes x cubed over 3. And then I have plus 2x becomes negative plus 2x squared over 2, so plus x squared. Just like that. Okay, so let's substitute. If I sub in 0, everything is 0. Now let's sub in -2, 16 over 4. And don't forget, this is the minus part, right? So 16 over 4, 4. Minus 8 over 3. And then 2 squares 4, minus 4. So this comes from the first region. And then second region, we have -1 over 4 minus 1 over 3 plus 1 minus 0, right? Everything becomes 0. So what do we have here? 4 minus 4 is gone. So 8 over 3 from the first region. The second region I have here I have -3 over 12 minus 4 over 12, -7 over 12, plus 1, 12 over 12. So that's 5 over 12. Common denominator is 12. 32 plus 5. Plus 5, 37. And that's it. Let's take a look at investigation number 2 from page 520, from page 523 together. So you're asked to draw the graphs of y equals the square root of x and y equals to x minus 2. Label out the region in the first quadrant, which is bounded by the functions and the x-axis. Okay, so we have the graph already shown here on the screen. And then we want to label the region only in the first quadrant. So we're talking about this part here. Okay. Number 2. Why is it not possible to use the techniques you learned from investigation 1 to find the area of the region in R? Well, if you look carefully at the diagram though, this region that we're interested in is not exactly bounded just by the x-axis and also the two functions, because there is actually this piece here that is under, right? Under the x-axis. Then, what do we do with it? So that's why we cannot just, use the same method. So we need some other ways to find that region. Number 3, divide R into 2 separate regions whose areas are possible to find, and we will call it R1 and R2. Okay, so from what I'm thinking is that, well, since we know how to deal with the region that's above the x-axis, okay, let's get rid of this. Why don't we start from 0 and then call part of this green region R1, and then the next region R2 that ends over here. Okay. So from the graph that we have, we notice that region 1 starts from x equals to 0 and ends at the x-intercept of the line y equals to x minus 2, which is located at 2, 0. And then the second region R2 starts at 2 and ends at the point of intersection between the two functions at x equals to 4. Now let's find the area of region 1, which is marked between the x-axis, the function y equals the square root of x, between 0 and 2. Okay. So we have the integral from 0 to 2 of square root of x dx. This is x to the power of 1/2. So this is going to be square root cubed. And then times 2/3, evaluating from 0 to 2. That means I have the square root of 2 cubed. So square root of 2 times square root of 2 is actually 2. So 4 root 2 over 3. Region 2. This region goes from 2 to 4. And I notice that it is actually sandwiched between the two functions. So here we have square root of x minus 2. Okay. So I know that the integral of the square root of x is x to the power of 3 over 2 times 2 over 3 minus the integral of x, which is x squared over 2, plus the integral of 2 dx, which is plus 2x, going from 2 to 4. And now let's sub. 4 cubed square root, or the square root of 4 first. That's easier, right? So square root of 4 is 2, 8 times 2, 16 over 3 minus 4 squared, 16, 8 plus 8 minus 2 square root. So we know the first one is going to work out to 4 root 2 over 3 minus 4 over 2 is 2 plus 2 times 2 is 4. What do we have here? So the positive 8, negative 8 goes away. And then 4 minus 2 is 2 minus 2. So 16 minus 4 root 2 over 3 minus 2, or 3 times 2 is 6, so minus 6. So 16 minus 6 is 10. I have 10 minus 4 root 2 over 3 for region 2. In total, it will be 4 root 2 over 3 plus 10 minus 4 root 2 over 3. Oh, that's nice. Which is 10 over 3 square units. So we say that when a region R is not entirely enclosed between two functions, we have to make sure we partition the region R into subregions before we work out the definite integrals.